Okay, so what if there were no MIT? Well, then there also might not be an internet, or email, or Ethernet, or a place for all those digital things you like to store in some cloud. You'd also have to give up holograms, a spreadsheet, 3D printing, GPS, and those cool computer-generated explosions in some of our favorite movies. You'd need to give back X-ray, handheld calculators, disposable safety razors, secure online shopping, HGTV, optogenetics, the solar house, microprocessors, Jack Flory, and, well, there'd be a whole lot less biomedical engineering. Theoretically speaking, we're going to need to forget Theory X, Theory Y, Chaos Theory, Black Shoals, Little's Law, quarks, computational origami, modern meteorology, and linguistics. There'd be way less artificial intelligence, and for that matter, a whole lot less real intelligence as well. You need to do without the queen of carbon science, the father of modern economics, and the leaders of the European Central Bank, banks of Israel, Chile, Cyprus, India, England, and the U.S. Federal Reserve. We will need to eliminate some languages, like Java and C#. Forget about text-speech recognition. Erase your texts and assume your phone is no longer as smart. We may as well go back to the first machine age. You would miss out on the first African-American architect. And there would be so much to unimagine and undesign. Rockefeller Center, the Lincoln Memorial, and that cool glass pyramid at the Louvre. We need to put an X through edX, MITx, and MIT OpenCourseWare, which would help to uneducate over 100 million people and delete that online education revolution. By the way, we're also going to need to give up our national water quality standards and sewage treatment. We'll unlaunch 9 flights to the moon, 6 lunar landings, 3 manned Skylab missions, and the future of space travel. There goes our understanding of nanoscale and our ability to see through brains. We'd have to unmap much of the human genome. We no longer have the first woman to chair the U.S. Nuclear Regulatory Commission. As a side note, we need to give up the DC-9, DC-10, F-15, printable robots, biomechatronics, liquid metal batteries, artificial skin, rayon, radar, metallurgy, solid-state transistors, CT scans, and condensed soup. Of course, this is just a partial list. An actual list would be exponentially longer and ever-growing. But fortunately, we don't have to give progress back. MIT is here. Our ideas never stop, and our ability to innovate is infinite.
Hi, this is Amy Shao, class of 1996, course 3. At MIT, I lived at McGregor G entry, and Killian Court was my favorite spot on campus. Now I call the rolling hills, country roads, and red sand beaches of Prince Edward Island my home. Welcome to Canada.
Bonjour, je m'appelle Bob Schaffel, classe de 71, cours 4. Je suis le président du MIT Club de Montréal, ici avec mon ami le professeur Tim. Nous vous souhaitons une chaleureuse bienvenue au Canada. Hi, Bob Schaffel, class of 71, course 4, and president of the MIT Club of Montreal. My friend Professor Tim and I wish you a very warm welcome to Canada.
Hi, I'm Carly Buchwald, class of 2007, course 12. While I grew up in Massachusetts and stayed there through grad school, living there a total of 27 years, now I am a professor in Halifax, Nova Scotia. Welcome to Canada.
Hi, I am Andrea Doria. I am an MIT EMBA-19, senior scientist and research director at the Hospital for Sick Children in Toronto, Canada. I hope you are able to enjoy the event. Come over.
My name is Don Ritter. I graduated in 1988 in the graduate program in course 4 from the Center for Advanced Visual Studies and the MIT Media Lab. I'm now living in Montreal. Welcome.
Hi, my name is Laura Turcolet, course 5, class of 1998. Although I loved every minute of my days in Cambridge, today I call Halifax, Nova Scotia home. Welcome to Canada.
Hello everyone, my name is Carlos Gutierrez, class of 2012, course 1. Welcome to Canada.
Hi, I'm Simon Van Norden, course 14, class of 1989, coming to you from beautiful Montreal. Hope you'll have a chance to come by and visit us sometime.
Good evening, and thank you to all my fellow Canadians across the country for that warm welcome as we kick off MIT's first virtual campaign roadshow event. I'm particularly grateful to the MIT community of Canada for hosting us tonight, and I'm pleased to note that all of our speakers during this first session have Canadian ties of their own. I'm sorry we can't be together in person tonight. On the bright side, holding tonight's gathering virtually gives us a chance to bring together an even broader group than we might normally. We have over 3,500 people expected to join us tonight from 80 countries around the globe, a great MIT gathering. Our topic tonight, Science and Discovery, lives at the heart of MIT, which excels as an unparalleled hub of scientific research and innovation. Institute researchers are plumbing the secrets of the universe, modeling climate at a local, regional, and global scale, striving to understand how brains and bodies give rise to cognition and mind, and racing to find treatments and cures for diseases ranging from the acute, like COVID-19, to the chronic, like cancers and maladies of the aging brain. President Rife reminds us that we are a community with, quote, a passion for tackling humanity's hardest problems together. At MIT, we believe science is a team sport, that creative friction at the boundaries between disciplines is fertile ground for new discoveries and innovations. Our response to the pandemic reflects exactly this approach. Hundreds of faculty and students across the Institute in disciplines ranging from chemistry and biology to mechanical engineering and design, to economics and management, to computer science and artificial intelligence and machine learning, all have built teams that leverage MIT expertise, recombining and remixing their skills and resources to develop new equipment, test methods, triage strategies, therapies, and a fundamental understanding of the virus and its mechanisms. In facing these challenges, we rely, as we always have, on the support of alumni and friends. The global MIT community responded to this crisis, providing both encouragement and tangible support. At the peak of the first wave of infections in Boston, alumni from around the world arranged shipments of PPE and provided generous financial support to enable MIT to help its students and faculty continue their studies and bootstrap new research projects. As one of our alumni recently commented to me, this is MIT's moment. An appreciation for both intellectual understanding, MENS, and practical application of that knowledge in the world, MANUS. It's baked into who we are. We do not shy away from tough problems, as daunting as they appear. We seek to know more and to turn that knowledge into know-how. We value ideas and solutions. The commitment to living these core values has been expressed clearly by MIT's pivot to tackle COVID-19. Jumping into action, faculty and students redirected research to create novel, inexpensive design for face shields, to assess effectiveness of masks and mask material, to discover ways to detect and treat the virus, and to model the impact of public health methods on the economy. We're proud to be mission-driven. Indeed, like that of any great research university, MIT's mission directs us to educate students and advance knowledge. When MIT faculty pursue this mission, they change the way that we look at the world, they launch disruptive new industries, and they help shape, support, and educate amazing students. It's vital, this work that we do. But unlike most schools, our mission statement does not stop there. It calls for MIT to educate students and advance knowledge, not just for their own sake, but to serve the nation and the world for the betterment of mankind. It demands that we use our knowledge to tackle humanity's greatest global challenges, and we embrace these obstacles because we know that the people of MIT can deliver and make a better world. To support that dream of making a better world, in May of 2016, we launched the MIT Campaign for a Better World, a campaign focused on core priorities and new opportunities, aimed at bringing the most talented faculty and students to MIT and empowering them to accomplish that mission. Many of you have told us that your own generosity to MIT in the campaign has a very simple inspiration. You have seen that a gift to MIT is truly a gift to the world. What makes this true is that to the people of MIT, humanity's urgent challenges are actually invitations to action. From our unwavering commitment to scientific discovery, to our zest for innovation and collaboration across disciplines, MIT is turning promising theories into practical solutions. We are focused on ensuring that everyone in the world can benefit from improved healthcare and increased access to life-saving treatments, from brilliant design and breathtaking artistic works, from clean energy and clean water, from computational innovations and nanomaterials, and from the insights into the natural world that fundamental research provides. While we strive to make a difference now, MIT is also firmly focused on the future. Our objectives for MIT and the aims of our campaign for a better world are bold. We aim to create the next generation of highly trained thinkers and doers who will offer the world both technological proficiency and the cultural, ethical, and historical consciousness to use technology for the common good. The campaign goals are not abstractions. These scholars and inventors need the resources, scholarships and fellowships, laboratories, living spaces, to provide them the degrees of freedom to reach across disciplinary boundaries and invent new fields. Enabling them to do their best work, pushing the boundaries of what we know, will take the dedication, participation, and support of MIT's alumni and friends. Many of you here with us tonight have joined in this effort already. As of today, the MIT community has come together during this campaign to raise more than $5.7 billion from nearly 110,000 donors around the globe. And by the way, that's US dollars, not Canadian dollars. On behalf of MIT, I would like to thank all of you. To make a better world, we focus on creating and applying knowledge and educating future leaders. Tonight, we are going to dive into MIT's dedication to discovery, the pursuit of knowledge through basic and applied research. Later this evening, you'll have the opportunity to join breakout sessions with MIT faculty and staff who will share highlights and news from across the Institute. Topics include news and updates from Sloan and the MIT Alumni Association, and sessions with faculty exploring the politics of molecular medicine, the Mars 2020 mission, and CRISPR technologies. You can find information about all of the breakout sessions, including the Q&A session, on the agenda page of the event website. But first, you'll hear from 3 MIT scholars who will discuss their work and then join me in a panel discussion of questions you'll be able to submit. We will hear from Rebecca Saxe, the John W. Jarve Professor in Brain and Cognitive Sciences, Linda Zhong-Johnson, a graduate student in the lab of Professor of Microbiology Tony Sinskey. And to get us started, we have Nergis Mavalvala, the newly appointed Dean of the MIT School of Science and the Curtis and Kathleen Marble Professor of Astrophysics. Nergis, I'll hand it over to you.
Of course, we all know we can never violate the laws of nature, or at least that's what we've been told. But what if I told you that we can sometimes manipulate them to our advantage? I'm Nergis Mavalvala, and as part of my work with the MIT LIGO team, I'm looking for ways to ever so slightly bend the laws of nature to help us explore the dark and warped side of the universe. Humans have been looking out at the stars for millennia, but it wasn't until Galileo built a telescope in 1601 that we could see much further out into space than our naked eyes would allow. And that was a paradigm shift. With increasingly more powerful telescopes, we have revealed a universe with light that is vast and amazing. But how might we see objects that don't emit light? If we want to see objects like black holes, we must use some other property of theirs that isn't light. That property turns out to be their gravity. And gravity has a messenger, gravitational waves, ripples in the very fabric of space-time itself. LIGO detects these gravitational waves with laser interferometers that have sufficient precision to measure the motion of mirrors that are 4 kilometers apart, moving by about 1,000th the size of a single proton as the gravitational wave passes through them. In 2015, we saw the first direct signatures of gravitational waves from 2 colliding black holes, and that was thrilling. Then, in 2017, we saw something equally profound, the collisions of 2 neutron stars. Neutron stars are the cousins of black holes. When black holes collide, the only thing that's given off is gravitational waves, usually. And that's because black holes are black. Even light can't escape their gravitational pull. But neutron stars are a whole nother thing. They're made of neutrons. When neutron stars collide, their gravitational wave emission is accompanied by a spectacular light show. So, on this particular day in August 2017, LIGO saw gravitational waves from a neutron star collision. We were able to identify that the collision occurred at a location in the sky that could be observed from the southern hemisphere by telescopes. It was daytime there at the time we made the detection, so scientists had about 11 hours to prepare to look for this new object in the sky. And that night, over 70 telescopes pointed at that part of the sky where LIGO had seen the gravitational wave emission, and they found an entirely new object. When neutron stars orbit each other, they're dark. But when they collide, boom, there is an enormous flash of light, and that flash of light can last days, weeks, months. When scientists measured the light, we saw something amazing. From the different colors of light emitted, we saw elements of the periodic table being fused in real time. And this helped us solve a long-standing puzzle of where heavy elements like gold and platinum come from. We discovered that neutron stars are the factories where these heavy elements are manufactured. And that's not all. Until now, we have thought that we, this planet, we humans, that we're made of stardust. But now we know that we are really made of neutron star dust as well. But just seeing ones and twos isn't enough. A black hole here, a neutron star there. That's a little bit like aliens coming here to the Earth and meeting one human and concluding that all humans are like this one human. So we have to measure many such systems to understand their properties. And I look for ways to make the LIGO detectors we use to detect gravitational waves even more sensitive. But when we try to do that, we come face to face with one of nature's most fundamental properties, quantumness. Quantum uncertainty demands that no matter how clever you are with your apparatus, how good of an experimentalist you are, your measurement must be uncertain. And that's what happens with LIGO. Quantum uncertainty meddles with the measurement we're trying to make. How? Well, LIGO measures the positions of mirrors using laser light. You shine a laser beam at a mirror, the mirror reflects the light back, you measure how long it took the light to travel, and you can measure the distance. Essentially, the wavelength of the light is like the tick marks on our ruler. My group works on ways to get around these limits on our quantum ruler, limits imposed by nature. Basically, we ask, how can we make LIGO more precise by tricking quantum mechanics, even though we can never actually violate the laws of quantum mechanics? The answer lies in a specially engineered quantum state of light called a squeezed state. Squeezed light is engineered in such a way that the spacing between the tick marks on our light ruler can be made more precise. Remember, quantum mechanics always makes you pay the price. And the price that you pay then is that the height of the tick marks on your ruler become more imprecise. They jitter up and down a lot more, but the spacing between them becomes more steady. Now, you can't do this ad nauseum because eventually the height of your tick marks will become so imprecise that it will sometimes go to zero, and now you have little to measure with. But this is what quantum mechanics does. It allows you to use special tricks where you can reapportion uncertainty from, in our case, the spacing between the tick marks of our ruler to the height of the tick marks and vice versa. And that lets you make a more precise measurement. We make these squeeze states of light in our lab, then we inject them into LIGO, and voila, we have a more precise measurement of gravitational waves. And in fact, this has worked out really well for us. Since we got our squeezer working, LIGO went from measuring about one astrophysical event per month to over one per week. Now we're not just measuring a handful of events here and there, we're already seeing things that we've never seen before, and they're quite unexpected. This is what comes from discovery. You just keep asking the next question. You don't discover something and then pack up and go home. You've just figured out the next question that needs to be asked, and you keep going. We have close to 100 detections so far, and we're gonna keep going. Now, having had this joy of discovery in my own work makes me want to bring this experience to scientists everywhere. And bringing that joy to my colleagues and students in the MIT community, that's something I love in my new capacity as dean, to enable the science of others, to make discoveries possible for all my colleagues, for our students, and for the MIT community. I hope you also share my excitement about the future of science. Look, this is a time when science is under attack, and we all need to share our excitement about science with anyone who will listen. To me, the world is enormous. It's a vast world out there. And for us to make a better world, we must first understand that world. And at MIT, that's just what we do. Thank you.
Tonight I'm going to tell you a story about one recent study. In the fall of 2017, Livia Tomova came to work in my lab. I'm Rebecca Saxe, and my lab uses brain imaging to study human social cognition. As a young child, Livia and her family were political refugees, escaping from Slovakia to a refugee camp in Austria. Years later, when she did her PhD at the University of Vienna, she chose to study how stress affects social motivation. When people are stressed, do they become more generous and empathic or less? Obviously, this is a really important question, but to test it, she used standard experimental approaches, like making people do a math exam or give a talk without seeing the audience. But these kinds of temporary stresses are small. It might be hard to disentangle from the pretty high levels of background stress that college students already experience every day. So anyway, when she came to MIT, Livia and I talked career strategy. She could continue in the direction she was already going, or she could take a big risk, a big leap, try something entirely new, something no one else had tried. A week or two later, Livia had a pitch. She proposed that we study how the human brain responds to social isolation, whether people who are acutely isolated crave social interaction, the way that people who are fasting crave food. This project ticked all the boxes. It was new territory. We didn't know how much isolation would be enough to test the idea. Would people miss social interaction after being completely alone? No in-person or online interactions after 6 hours or 10 hours, or only after much longer? In 2017, 10 hours seemed like the longest we could feasibly isolate people, because who would consent to isolation longer than that? And it would be logistically hard. We'd have to figure out how to isolate people for a whole day. We furnished a windowless room with Tetris and Sudoku, a sofa, and a fridge full of food. To image people's brains without stopping the isolation, the participants had to learn to get themselves into the MRI scanner alone, while a masked and gowned researcher silently watched. It would also be technically hard. The brain region that shows craving responses to food after fasting, the substantia nigra, is really tiny and deep in the midbrain, a place that is notoriously hard to measure. I've been a professor at MIT for 14 years, and I had never done anything like it, and no one had. The project had just one weakness, I thought. Would it ever matter to people's lives? Why would perfectly healthy, well-connected people ever become socially isolated? The project might have no practical applications. 3 attempts to get the government to fund it failed. But sometimes we do science just out of curiosity. So Livia and I decided to go for it. Livia and a devoted team of MIT students conducted this experiment with 40 people. Each person had 3 brain scans, one on a regular day, one after fasting, no food for 10 hours, and one after isolation, 10 hours alone in our room. Like previous studies, we saw higher activity in substantia nigra when hungry people looked at pictures of food. But what no one had ever seen before was we also saw higher activity in substantia nigra when isolated people looked at pictures of social interactions. Some people have asked me if this explains why everyone on Twitter was so obsessed with food early in the pandemic, and I don't think it does. The substantia nigra, and indeed the whole brain, responds really differently when food versus social interaction has been deprived. And other people have told me they thrived in lockdown. They loved the break from social interaction. And our data show that too. Different brain regions responded differently to the experiment isolation, some people more than others. So we finished data collection in the fall of 2019. Over the winter, we started writing a paper. We had devoted more than 2 years to this project. Would anyone care? And that is how I came to be writing a paper in March of 2020 about how human brains respond to acute social isolation, the most timely and relevant paper of my life. The paper is now in press, coming out this month. Livia has started her next job at the University of Cambridge in the UK, studying social isolation in adolescents. Maybe surprisingly, these days teenagers report the highest levels of loneliness and isolation of any age group. The project raised more questions than it answered, as good scientific projects tend to do. How well does video chat replace in-person interaction? And Livia's original question still matters too. Does the kind of isolation and stress we've just lived through tend to make people more generous and empathic, or less? These kinds of questions are what we need MIT science for.
I'm one of those people who sticks firm to my decision once it's been made. For me, it was to do research in oncology. My mother had cancer when I was in high school, and I was sure oncology was my path. But then, in one moment, you suddenly realize you want to turn in another direction. I'm Linda Zhong-Johnson, and I'm a graduate student in microbiology at MIT because I had that moment, and I turned in a different direction. Right after I graduated from the University of Toronto, my mother took me on a cruise to Alaska to celebrate. And what I saw in Alaska just blew me away. I grew up in Hangzhou, China, and the rivers and streams I was used to seeing looked like this, rather polluted with plastic trash. When I immigrated to Canada, it was obviously much better, but you can still find plastic trash along the riverbanks. It never bothered me, it's just the way it was, the way I was used to seeing things. Pollution seemed like the natural part of life. But on that trip to Alaska, I saw this pristine and beautiful scenery. It was so clean, so clear, it was inspiring, and it just hit me. This is the way our environment is supposed to be. And then I realized, okay, you know what? Everyone works on cancer research, and that's really great. But perhaps they don't really need me. If I want a better world, the problem I need to solve instead is figure out how to get rid of plastic waste. Because yeah, you can try to recycle this water bottle, but basically all that does is delay when the materials end up in a landfill, or worse. The materials are lost, and we have to make new water bottles from petroleum. We ultimately add more plastic waste every year with the recycling strategies we have. We need a better one. And I also noticed there weren't many people working on the problem of how to degrade plastics using biology. So just like that, I changed the course of my life. I applied to MIT microbiology because of the interdisciplinary program and the range of professors at MIT interested in solving problems using biological engineering. For one, Professor Sinskey actually pioneered the field of biodegradable plastics back in the day. So, for the non-biochemists out there, what that means for my research is figuring out ways to use enzymes, these little proteins that speed up chemical reactions. and finding ways to use enzymes to basically eat up and break down a material of some kind. It works by attacking the polymers, the long strings of repeating units that form the material. With the right enzymes, you essentially disintegrate the original substance. Say you splash some gravy on your blouse or some red wine on your slacks. The polymers in a stain like that are short. There's lots of space between the polymers and they're accessible to water and thus to enzymes. So when you use your enzymatic laundry detergent on stains like that, the enzymes get in there, chew up the stain, and don't harm the fabric. And your stain is gone. But it's much harder to do when the product is entirely made of insoluble polymers, such as PET plastic or polyethylene terephthalate, which is the type of plastic I'm studying. That's the plastic you find in water bottles and takeout containers and those clamshells your cherry tomatoes came in. That plastic has polymers that have hundreds of repeating units, and there are many of these polymers packed tightly together around themselves. There's essentially no space for an enzyme to get into, and no water in between the polymers. If the plastic product is meant to hold water, that's pretty great characteristic. But it's a terrible characteristic if you're trying to disintegrate the bottles using enzymes. The only point of attack is the surface of the material. So I thought when I first started that all I really had to do was find the microbes that break down PET, because microbes are amazing and can adapt to eat all sorts of food, and harvest the enzymes that broke down PET. From there, we could recycle and reuse its components to make other products. No more landfill stuff with these bottles and food packaging. It was such a compelling idea. Good thing I had no clue then how hard this problem would be to solve. Because here's the thing, scientists know that enzymes can catalyze all sorts of chemical reactions. We know that the hotter the reaction, the faster they work. But enzymes are fragile, and if you raise the temperature too much, even by 1 degree, they unfold, essentially falling apart and losing its activity. But incredibly, we don't know how most enzymes actually work. We don't know the mechanism of the reactions. Most enzymes don't work at all on solid substrates because they can't penetrate polymer strands to get in and do their thing. So that's a problem if you're trying to break down PET water bottles and the like. To target and engineer the right enzyme to degrade the plastic quickly and cheaply enough to be commercially viable, there turn out to be 2 paths, and I'm working on both of them. The first is to create a random library of thousands to millions of enzyme variants and look for ones with improved characteristics. That requires a high throughput screen, essentially the ability to test thousands to millions of enzymes in a short amount of time. Without that screen, you can be testing your library one by one for the next century or so. It's a needle in a haystack problem. The second path, create a set of biochemical assays to measure the physical characteristics and mechanism of enzymatic PET degradation so we know how specific enzymes work. Then we can target our engineering efforts. I was able to develop one assay before the pandemic hit, which allows me to study variants of PET degrading enzymes and understand how different mutations are affecting enzyme behavior. Essentially, I'm deciphering where we made the enzyme better and where we made it worse. As of now, I'm discovering that some mutations aren't doing what others thought they were doing. Other researchers started looking at reactions after 18 hours. But with the new assay, I'm looking at it starting at 30 minutes. And that is important because the reaction starts right away, and you need to measure that too. So even in the midst of a pandemic, even when I can't do much of what I've been wanting to do, I still have tools and resources to work the problem, and we're getting closer to the answer. I'm grateful to be at MIT where we have the resources and the mandate to keep exploring. And the water bottles and lettuce containers you have at home, we know that they're not going away because manufacturers know they're good solutions for their products. And that's okay. My hope is that in the not too distant future, your plastic recyclables become truly recyclable, truly reclaimed and repurposed because of the ways we've come to understand the enzymes and apply them. That's the better world I see for all of us. Thank you.
Nergis, Rebecca, Linda, thank you so much for your time and the fascinating view into your work. From exploring the outer reaches of the universe, to charting the inner workings of our minds, to finding new methods and technologies to combat climate change, the work we heard about tonight embodies the MIT commitment to curiosity and discovery in the pursuit of a better world. To everyone who joined us for this inaugural MIT Virtual Roadshow event, I hope you learned as much as I did, And by the way, we won't have a quiz at the end of the session. I hope you'll stay with us after a break as we move into the next session of our program this evening, a series of concurrent breakout sessions. I invite you to return to your agenda and follow the links there to join each session for which you signed up during the registration process. And if you want to find out more about any of the sessions, you can always return to the main agenda page as well. Thank you again, and we hope to see you at our next event in February, where we will explore the topic, Innovations in Human Health. And we'll see you after the break. Thank you, Nergis, Rebecca, and Linda, for joining me in this Q&A session. And thank you to everybody in the audience for all of your questions in advance. I'm going to ask a couple of questions just to get us started, and then we will field questions from the audience. To submit your questions, please visit the polls tab, at least that's what I'm told to instruct you to do. To my three co-speakers, I want to remind you to unmute so you can do this. And since we all have ties to Canada in some way, I'm going to ask each of you to respond to this. Very briefly, how are you connected to Canada? And more importantly, who wins for coldest location? And I'll start. My hometown of Estevan, Saskatchewan, a couple of weeks ago, they hit a new daily low temperature for the month of October, minus 16.7 degrees Celsius, which I think is about 2 degrees Fahrenheit. And since I went and did my undergrad in Regina, I've been on the far side of the fixed point between Celsius and Fahrenheit many times. So Nergis, connections to Canada, and how cold have you been?
Yeah, so I'm an almost Canadian, and what I mean by that is my family immigrated from Pakistan to Canada when I was a student at university. So I was just a tad too old to be part of that. So Vancouver has been home for me in my college and university years, but I'm not actually Canadian. And so as you can tell, Vancouver, Canada, by far, they all went there because it was not too cold.
Perfect. Thank you, Nergis. Rebecca, connection and cold.
I was born and lived in Toronto until I was 18 years old, but I'm also fifth generation Canadian. I have great grandparents born in Canada. And I remember spitting in it, freezing before it hit the ground on the way to school.
Perfect. I love it. Linda, connection to Canada and how cold?
My mom and I immigrated to Canada when I was 9 years old. So I am Canadian and I don't speak Fahrenheit, but I think the coldest we've gotten when I was there is like minus 40 degrees Celsius. I don't think I win though, almost.
Linda, it's close enough and you've been at the fixed point of not through it. So we'll count that as being, it's a tie, and we'll treat everybody as being part of this. I'm going to take the questions as they come in, and I'm going to try and direct them as I can appropriately. Nergis, I'm going to start off with one for you. An audience member says that a researcher from Caltech has noted that due to the rapidly changing gravity within large weather storms, LIGO might have implications for storm detection. At what maximum distance from a LIGO interferometer could a Category 5 hurricane be located and detected? And would it enable LIGO to serve as an early detection system for tropical cyclones or tropical storms? And I'll let you decide whether to give the long answer or the short answer, but Nergis, if you could deal with that, please.
Yeah, so look, there is a long answer, but the short answer is LIGO is not very good at those kinds of things, in part because it's designed not to notice terrestrial effects. We're interested in the effects that are out in the universe, in the cosmos. So certainly something as big as a storm, just actually it's too big, it puts us offline. You actually go, so it really, no, it's not all that useful. We use all of the instrumentation to warn us of about to go offline things, but we don't use it for early warning. It wouldn't be very good.
Great, thanks. Rebecca, the next question I'm going to direct at you, and actually I'm going to save another one for later because I loved your description of tackling problems that didn't have a clear answer or didn't have a clear application. I'm going to come back to that. But in your talk, you also said the paper that you've written is now in press, and somebody in the audience would like to know when and where will it be published?
It's coming out in a journal called Nature Neuroscience next Monday at 11 a.m.
All right, so set your watches, folks. You'll be able to get it as soon as it comes out. That sounds excellent. And Linda, for you, again, a question from the audience. Is there a difference between breaking down harder items made of PET plastic, like water bottles, and softer items like plastic bags? And is breaking down one of them more challenging than the other?
Certainly. So generally, the hardness of the material is quite correlated with what we call crystallinity, which describes how tightly packed the polymers are. So harder materials tend to have tighter packed polymers, so that makes it harder just because the chains are less accessible to the enzymes.
Great. I'm going to insert one of my own questions here. We have more coming in from the audience, but I think all of you sort of raised this issue, and Rebecca, I know you did in particular, although I think all of you did, and that is the idea that fundamental research, basic science research, is really important. And I raise it because, unfortunately, today in the US, as we all know, funding sources are under attack around this. And I'm also reminded that sometimes it can be decades before a basic result, if ever, actually leads to an application. And that's not why we always do it. MIT's first Nobel Prize, if I have it right, I think was 1945 for the discovery of NMR, nuclear magnetic resonance. And it's probably 40 or 50 years before it led to an MRI machine, but that wasn't why people did it. So to all three of the panel, can you just comment on both the excitement you have of doing basic research and why it's important for a place like MIT to pursue it? And Nergis, you're the dean, the new dean, but you're the dean. I'm going to start with you. Thoughts?
Yeah, so look, I think the most important thing to know about most of the technology we use today didn't come from us imagining this is the technology that would come from the initial discoveries. I talked about quantum mechanics. Quantum mechanics has led to a complete revolution in everything from computers to almost every device you use. It was actually a rather obscure area of trying to understand the spectra of sunlight, for example. So I have to say that without exception, with very few exceptions, when you do fundamental inquiry, it will lead you to some understanding that maybe a decade, 2 decades later will be useful. So I can't say enough about how important that is.
No, but that's a great way of putting it. Rebecca, thoughts, comments?
Thanks, Eric. Yeah, I feel pretty passionately about this too, that, once we can see exactly what the application will be, we're almost at the point of engineering, and not to deride engineering, right? MIT is great at engineering, but there's lots of places and lots of companies, lots of industries devoted to the project of solving a problem once we know what kind of solution it needs. And what feels like kind of the distinctive purpose of having universities is that we can pursue problems that are much more open-ended than that, where we don't have to have it affect our bottom line in the foreseeable future, right? Where we can pursue the unforeseeable future. I think that's our special role in society and in the world. And so giving us a chance to do this role to our best of our ability, it means each part of the system is doing its job in making the world a better place.
Rebecca, I love that. Thank you. It's a great way of putting it, reminding us that all parts of MIT contribute to this. Linda, I'm going to ask you the same question. I realize what you described is more on the application side. It was certainly driven by a problem, but sounded to me like a lot of what you're doing is, in fact, those looking at just exploring the space of solutions to it. So from your perspective, just thoughts on this question of why are you excited about it, and why should MIT be the place to pursue fundamental research?
Sure. So I was actually initially driven by, just trying to get this enzyme to work and apply it to the problem. But during that process, I've come to realize just how important it is to understand how the enzyme works fundamentally to even try to solve the problem I'm trying to address. Most people, as I was reading through literature, is just like trying to find ways to make it faster, make it better. They don't really look at how the enzyme works. And I think how the enzyme works is really, really, really interesting. If we can understand just how one of them works, we can really answer a lot of different questions, because things that we will learn from PET degrading enzymes can maybe be applied to cellulasers. There's similar systems of solid state substrates and soluble enzymes. This field is got a lot of questions to answer that we don't have answers to. So it's very exciting.
No, that's great. Thank you. The next question, again, I'm going to direct to all of you, and I'll do it in some random order. MIT, at least for me, is a place where there are very few boundaries. In fact, the buildings were designed so you couldn't tell where one department ended and another started. In not almost, every department is at the top of its field. And so you've got colleagues that are experts at almost anything you wanted to explore. And that raises then the question of collaboration. And I'd love for each of you to give a sense of what you expect to see in terms of collaborations in the future, especially between scientists and practitioners, and how you think it might be different from what you see today. And Rebecca, I'm going to start with you.
I was worried you were going to do that. Well,
you can pulse, you can pause. Go for it.
Collaboration is obviously central to lots of science, and the particular experiment, the story I was talking about today, that story is certainly a story of collaboration, and that the inspiration to ask this question about social isolation came from a colleague in the McGovern Institute, Kay Tai. The solution for how to image such a small and difficult to reach brain region came from the director of the Imaging Center. So that project was, and then there's a bunch of MIT undergrads who are absolutely critical collaborators, right? Speaking of the future of science. So I think every project is a story of collaboration. The question you were asking is, how is the future of collaboration going to be different? I guess actually one thing we're learning about the future right now is that we're figuring out how to make the physical location of people a lot less important, right? That the pandemic taught us quickly that we could render virtual a lot of things we didn't think we could, right? We've managed to work with people who are in different places, in different time zones, to teach courses to people all around the world at the same time. And things that were incredibly daunting when they were the only way, then they suddenly were much more possible. So I guess what I see as the potential future for collaboration is better reach for the best skills and the best tools and the best minds wherever they may be.
Thank you, Rebecca. I love it. And as you were saying that, I'm reminded that I think many of us that have been around MIT too long are convinced that MIT undergraduates mostly operate on Hawaii time. So, the time difference isn't as crucial as you might think. Linda, thoughts on collaboration and how you think, why it's crucial and how you think it might change in the future?
I'm not sure if I can comment on how it will change in the future, but I do believe that it's incredibly crucial. Like my research itself, it's very much a biological problem, but also a material science problem. And it's not something that I have much expertise in. So I need to reach out to material scientists, chemists, and sometimes even economists, because eventually if we want to commercialize this technology, we need, economic analysis and end-of-life analysis for all that kind of stuff. So it's a problem that can only be solved through collaboration. I don't think I could ever understand all those things and do it all myself,
Sure you can. You're an MIT student, no problem.
Maybe.
Nergis, thoughts on it? Collaboration, crucial, and how might it change?
Yeah, so, I actually think that the biggest challenges facing us as a society right now that can and should be addressed by science and engineering and policy are going to be addressed by all of those three things in conjunction, whether you think it's climate change, or you think it's social media ethics, the ethics of computation, any of those questions, very big, broad questions that really no one discipline can or should try to answer. And therefore, I think that's really the way of the future. I actually think the era of sort of small, isolated, mad scientists working in their own lab or at their own desk is actually probably not that common anymore. And so I really do think the path of the future is looking at problems much more globally and more collaboratively. And like Rebecca, I actually think solving the question of physical location is, we've learned a lot from these last 10 months.
Yeah. And I'm going to come back to that. But again, thank you, all three of you. And again, I'm reminded that in my own career, I've had a lot of great collaborations, and often I'd have an argument with my chief co-collaborator about who had the best idea, and we both thought the other person did. That's the best kind of collaboration, when you're not worrying about the credit. Mm-hmm. All right, I'm going to go back to some individual questions, again, coming in from the audience, just in the order I'm seeing them here. Nergis, I'm going to start with you. We have a high school student in our audience who's asking for your advice about internship opportunities for high school students in the areas of astronomy and astrophysics, particularly gravitational wave analysis, which I know you know a ton about. Are there such opportunities that you can recommend?
Absolutely. So look, for high school students, at MIT, there is the RSI program. That's the Research Science Institute. That it's for it's a competitive high school program. But really, I'll tell you, in my group, every summer except this very past summer, we always have 1 or 2 high school students working with us, and they're usually local because you have to kind of have a place to live. And I work in a physical lab, but really, I would say reach out to the groups that you're interested in, or reach out to me and I'll point you to them, and find something local near where you live and jump in. And also, I'll say one other thing. Data analysis is actually computational, so you actually can do it from very many different places. You don't have to come to my lab. You can do it from your computer.
So Nergis, that's a wonderful answer, and I dread to think how much your email box is going to light up tonight with requests from around the world. But thank you, a wonderful way of putting it. Linda, the next question I'm going to direct to you, again from one of our audience members. How long do you think it will be before post-consumer recyclables can be reclaimed using the tools that you're currently exploring? Can we generate fuel from breaking down plastics, or reuse the materials to decrease the need to extract new ones? Something I'm sure you've thought about.
Right. Oh, I can't really predict how long it will take. People are moving quite fast in the field, but we are still facing a lot of challenges. And those challenges right now, basically degrading crystalline PET, so far, no one really knows how to degrade that. And that is a significant component of post-consumer PET materials. But what enzymes can do is degrade it down into its monomer constituents. So those can be harvested and used to make new PET. So yes, this technology can lead to theoretically infinite reuse of PET materials, depending on whether people will actually throw their trash in the correct bin. So that is a problem in of itself as well. So we may not be able to eliminate, let's say, pollution, but we can at least reduce it by a lot and reduce landfill. That's something that we can definitely do, or loss of materials through incineration, such that we have to get more materials from petroleum sources. Yeah. And there was something else, right?
No, I think it was, could we reuse it in other ways? But I think you've addressed it. So
yeah, totally. If you use microbes to engineer it, okay, so the molecules that you get from PET, enzymatic PET degradation, are organic. So they can be consumed by microbes, which can then be engineered to use those as carbon source to make anything that they can make, which is a lot of things.
Right, perfect. And Rebecca, for you, a question. Given most youth are now using social media, are they not more connected in a different way? Can empathy be studied using text messages from these social media platforms instead of the experimental approach?
Wow. So it is definitely true that teenagers are more virtually connected to each other than any previous generation ever has been. And it's as a result, that's part of what makes it so striking and surprising that they report higher than ever levels of loneliness. So loneliness is not itself a measure of how much social connection you have. It's whether both the quantity, but more importantly, the quality of your social connection feels that it satisfies your needs. And so in the question says, can we just observe what's going on? Well, yeah, sure, we can observe what's going on. And if we observe what's going on, it looks like having lots more virtual connection is not making people feel less lonely. But that doesn't, of course, mean that all virtual interaction is bad, or no virtual interaction is ever good for fulfilling social needs. Actually, the little bit of research that exists suggests it, of course, depends hugely on what you're doing through your social media and what you're doing through your tweets and your video chats. And it matters for humans of every age. This is not specific to youths. Again, another thing we found out in the pandemic is even grandparents can use Zoom and Twitter and text messaging to stay in touch with their grandchildren if that's what it takes. So most of the research that has been done, again, this is a very new field, suggests that this kind of thing that we're doing here, where it's live and online, where we're giving each other visual and auditory cues, that we're responding to each other, that's pretty good for fulfilling a lot, though not all, of human social needs. And it's much better doing this than, for example, just looking at people on Facebook or looking at people on their Instagram, which evokes lots of processes of social comparison, tends to make people feel worse about themselves, and also doesn't fulfill the sense of being heard. So those questions about how is it affecting adolescents and how can we make the use of social media better rather than worse is part of the directions that Livia, the person who started this whole research program, is now going at her new job at the University of Cambridge.
That's fantastic. Thank you, Rebecca. It really gives a great sense. I'm going to question now for all three of you, and one that I'm sure you've all been thinking about. How does the COVID-19 isolation affect your ability to perform your research? And Nergis, I'll start with you, and we'll just go through the three of you.
Yeah, so look, I actually have a pretty active lab, and we build things, and so for a while the lab was shut down. Now we're in a place where I'll tell you a little fun piece of my life. So being an older professor now, I'm rarely allowed into the lab by my students lest I break too many things. But during the pandemic, my quota is 1 hour per 24 hours in the lab. So at any given time, if I'm working with any of my students, I get 1 hour per day in the lab with them, and that gives us enough social distancing, etc. And it's actually been really great because I have this quota. I try to use it, so I've actually been in the lab more than I was before.
That's great. And Nergis, I'm sorry, but talking about yourself as an older professor, how do you think it makes me feel? But we'll let that one pass. Linda, how's COVID-19 isolation affected your ability to do your research?
Right. So when I first was allowed back on campus, we were at 25% research capacity. And as a biologist, that's kind of really tricky, especially because whenever I need to purify an enzyme to do an experiment, I basically use more than 25% of the allotted time that I'm allowed. So at first I wasn't doing anything, and I couldn't, if I started, I wouldn't be able to finish it. So I just was reading mostly at home. But once we reached 50% hours, I was like, good to go. And now it's not too different. My lab is small in general, so there's not much space constraint, so that's been good. What's really been hard though is sometimes I've been trying to start off a new assay to study the enzyme, and that I needed somebody in a different department, though close to me, but in a different department to help me with the instruments. And I don't think he's allowed in lab because his work is not experimental, so then I haven't been able to proceed with that. So I'm hoping once the pandemic ends, or once he's able to be back in the lab, that we can work it out. But the room is super tiny, so only one person's allowed in there anyway. So I don't know how that's gonna go. Yeah.
So it's a challenge, I get it. Yeah. Rebecca, how are things affected you?
So the research I talked about here was research on adults, but a big chunk of the research that we do in my lab is actually on babies. We study baby brain development, baby psychology and cognition. And we had a whole bunch of studies going on scanning baby brains. And we certainly haven't, since February, we haven't been able to bring families with babies into the lab, so we can't do brain scans. But actually, really excitingly, a bunch of the really talented grad students and postdocs in my lab figured out how to study baby behavior over Zoom using video chats. And so we now have a super productive research program going. We're studying babies, and there's this benefit we didn't see, which is lots of families who couldn't have made it to our lab for all kinds of reasons. They live too far away, they couldn't afford the time, suddenly can participate in our research. And so not only are we being productive, but the research population is more diverse and representative. And so we achieve many of our goals as scientists and as human beings better now than we were before.
That's great. Unfortunately, we're almost out of time. And so if we didn't get to one of your questions from the audience, I'm sorry. I want to thank Nergis, Rebecca, and Linda for a great conversation. I've tremendously enjoyed this. And I noticed We've all been away from Canada too long. We didn't put an A at the end of any sentence here. So, you know, we're going to have to go back and practice on that. But thank you to the audience. Thank you to my three colleagues for just a great discussion. We hope you'll stay as the audience and participate in the next round of breakout sessions, which is set to begin in just a couple of minutes. And we certainly hope to see you at the next one of these MIT events, and enjoy the rest of your evening. Thanks, everybody.